Hi guys, in this video let's talk about a problem different bits sum pairwise. So this problem is also by the name Hamming distance. So basically it was asked in Google, in one of the interviews of Google. So let's see what the problem says. So we define f of xy. F is a function that takes two parameters x and y. So it defines as the number of different corresponding bits in binary representation of x and y. So f of 27 is equal to 2. How? So 2's representation in binary is this and 7's representation is this, and both of these numbers differ at 2-bit position. So first is this and second is this, right? So therefore the answer is 2. Now you are given an array of n positive integers from a1 till an. So you have to find the sum of f of ai comma aj for all pairs I and j such that ij lies between 1 to n, and you have to return the answer modulo 10 to the power 9 plus 7, right? So basically you are given, in this case if you'll see, you're given 1, 3 and 7. So basically what you have to do, you have to find f of 1, 1. How will we find f of 1, 1? So it's nothing but represented 1 in this form. Then again, how many bits differ? No bit, right? So it'll give us 0. Now what about f of 1, 3? So this is 1, right? And 3 is this. So there is just one position at which both numbers differ. So therefore it will give us 1. What about 1 and 5? So I have 1 and 5 is there. So there is again just one bit position at which they differ. So again it will give me 1. Now I have to find for 1 and 5 and 5 and 1 separately, right? That means they are counted different, okay? And also I have to find for 1 and 1, 5 and 5, 3 and 3, so I'm talking about this particular array. So basically if I have some I and j, then I have to calculate for both I, j and ji. They are considered separate, as well as I have to calculate for I and I as well, right? So now let's see what we can do about this problem, right? Let's see what we can do about this problem. So the brute force approach says that we can pair up every element and find number of different pair of bits, right? So basically I can pair up every element, right? So I can have 1, 1. So what are the pairs? So these are pairs are already written: 1, 1, 1, 3, 1, 5, 3, 1, 3, 3. So I'll take them separately and then I'll go over their bits, and then I'll find that okay, they differ at these many positions, and I'll return. So if I'm pairing up every other element with every other element, so I'll get the time complexity of order of n square. But let's see if we can do better than this. So let's talk about the optimized version. For that, let's build some intuition. So basically, we are saying that we want to count the number of ones, right? So basically, we want to count the number of bits that differ, right, at every place. So I have, let's say, I places. So I have 0, 1, 2, 3. These many places are there in some number. So I have right now my array is, let's say, so let me erase all of this. Let's say my array is 135 only right now. And so here I have 001, here I have 011, and here I have 105. So that 101. So basically what I have to do, I have to check okay, for every pair I have to check at what ith positions the bit differ. So I want to check that if at some position bits differ or not. Now how can I check that? So basically if I find the XOR and if I get 0, I know that means the bits are same, right? So bits are same, but that is not of my use, right? So I want to find where bits are different. So basically bits will be different, 0, 1 or 1, 0, when my XOR will be 1, right? When my XOR will be 1. So I'll be trying to XOR the bits and I'll look that how many ones are there, right? So if I would have given, let's say, 0 and 1 only. So if this is only my number and the binary representation of them will be this only, right? So now I'll simply XOR it and I'll get 1 and I'll simply return 1. But now let's say I have 0. So I have only single 0, but now I have, let's say, 3 ones. Okay, I have 3 ones. So 3 ones are there. So I'll do what now? So I know that one pair of 0 and 1 will give me 1 bit. It'll tell me that if there is one pair which is 0 and 1, it'll contribute to 1 bit, right? That it differs by 1 bit. So now it was included for one pair. So here I have 1 0 and let's say 3 ones. So what I'll do now? So I'll associate the 0 with 1. So now I know I want to find the different bits. So I'll be pairing up a different bits, right? I'll be pairing up 0 1, right? 0 and 0 and 1 won't be of use to me. So I'll be pairing the 0 with this one, then the 0 with this one, then the 0 with this one. Essentially, what am I doing? I am trying to find the number of zeros, how many number of zeros are there, and I'll simply multiply it with the number of ones that are there, right? So I'll simply multiply it with the number of ones that are there, right? So basically, if I have 3 zeros and 2 ones, so what I'll be doing? I'll be associating every 3 zeros. I'll be associating all the 3 zeros with all the ones, right? I'll be doing this, isn't it? So I'll be associating all of them. So essentially, I'm multiplying. So 3 into 2, that means 6. 6 times they'll be associated, and that means 6 number of ones will be there, right? So essentially, now what can we do? Instead of forming the pairs, I was given 1 3 5. Instead of forming the separate pairs, right? Instead of forming the separate pairs, what I can do is I can simply represent them in binary form. So what I'll get for 1 I'll get 0 0 1. For 3 I'll get 0 1 1. Then for 5 I'll get 1 0 1, right? So what I can do is I can simply go to every bit position, and I can count the number of ones and number of zeros. Then I can simply multiply them up, because each of those pair will be contributing one, right? They'll be contributing 1 to the answer. So I have this ith bit as 0 1 2. So let's see with the example. Okay, let's see with the example. So basically, let's consider the bit position 1. Okay, let's consider this part. Let me change the color. So let's consider this part, right? So I have 0 1 and 0. So if I were taking them separately, so let's say if I were considering 1 and 3, so ith bit of 1, so 1th bit of 1 and 3 is nothing but it's a 0 and 3 is 1, right? So now it will give me the XOR of 1. That means these bits differ, right? And if I'll be taking for, let's say, 1 and 5, so here I have 0 and in 5 I have 0, so they give me 0 because they don't differ. Now if I have 3 and 5, so here 3 is 1 and 5 is 0, so they give me 1. That means they differ. So since I'm associating every 0 with every 1, so I'll simply count the number of, at every ith position, I'll simply count the number of 1s and number of zeros. So here my number of zeros is 2 and my number of 1s is 1. So I'll simply do 2 into 1. That will give me 2. Now I also have to multiply it by 2, because since I'm considering just not 1 and 3, but I'll be considering 3 and 1 also, right? So therefore they'll give me same result, right? So I'll simply multiply it by 2. So I'll be calculating for this bit position, whatever be my answer, then I'll be adding it to this bit position, whatever be my answer, then I'll be adding to this bit position. So essentially I'll be adding all the answers bitwise. I'll be checking all the answers bitwise. So let's see the pseudocode for this. So pseudocode goes something like this. So basically I have defined my mod, because I have to do mod the answer with this at the end. So I'm given an array A, right? That will have the numbers that I have to find the hamming distance for. So initially my answer is at 0. Now I have kept a count for counting the number of zeros and number of ones, right? So here I have a count variable. So I will traverse to all the bit positions. So I am considering here that my integer is of 32 bit. Right, so I will be iterating to all the 32 bits, right? So it will start from the 0th position and it will be moving to most significant bit position, right? So from 0 to 31 I'll be going. Then my count is initially 0, and then I'll be iterating over my given array, right? Then simply I'll be checking that what all bits are set. So in case of 1, right, so its 0th bit is set. So this will essentially give me what? This will give me, so AJ in this case is 0 0 1, let's say. So I have 1 3 and 5 with me. So let's say AJ in this case is nothing but 1, and 1 left shifted by I, that means 1 left shifted by, sorry, so this shouldn't have, no, it's right. So basically I is 0, right? So 1 left shifted by 0, it gives me what? It gives me 1 only, right? So I'll have this. Now it will give me 1, that means this bit position is set in this number, so it will give me true, and I'll simply count. Now my count becomes 1, right? So I'll simply iterate it over for all the elements. Now I'll go for my j will become 1, and I'll be going to 3. So now I'll check that, okay, 3 is this, and again 1 left shifted by 0, it'll give me 1 only, right? So I'll get 0 0 1, and again this will give me what? This will give me 1, that means this bit is set, so this will return me true, and I'll simply increment my count to 2, right? And at the end of iterating all these elements, after checking there the unit positions bit, right, then I have my count of the number of ones, right? And the count of the number of zeros will be nothing but number of elements that are there in the array minus the count. So that will give me the count of the number of zeros. And since we have seen previously that if I multiply them together, then I'll be associating every 0 with every 1, and that will give me the set bit, right? And I'll be multiplying that with 2 because I'll be considering ij as well as ji separately, right? And then I'll be adding that to my answer, and I'll also be doing the modding it with the mod, which is here I have taken, and then I'll simply return my answer. So this is the approach, and the complexity is going to be nothing but this loop will run for 32 times, so it's going to be 32, and this loop will run for the number of elements in the array time, so that means n, so it's going to be 32 into n. So thank you so much.
Hello everyone, let's talk about a new problem, that is single number 2. What does this problem exactly says is that you will be given an array of integers, and in this particular array every element is going to appear thrice except for one element which is going to appear only once, and your task is to find that particular element which does not appear thrice. I hope the question is clear. Let's look at an example now to understand it better, right? The first array contains all these elements, right? And in this array, you will see that there is only one element, that is 4, that is appearing only once in this particular array. So for this array, for this first example input, the output is going to be 4. Now, for the second example, you will see here that in the given array, there is only one element that is appearing once, and that element is 1. And this element needs to be returned. So for this particular question, the output is going to be 1. Now, let's try to make some observation to see how we will solve this question, right? Now here, let us look at every bit position. Here, you will see that every number that appears thrice will either contribute to 3 ones or 3 zeros to that particular position, right? Also, the number that appears once, let's say that number is x, will contribute exactly 1 0 or 1 1 to that particular position, depending on whether it has 0 or 1 in that position, right? So let's take an example to understand this. Let's say the array elements are 4, 4, 4 and 2, right? So if I write the bit values of these numbers, I will get this, right? So here you will see that since 4 is occurring thrice, it is contributing to 3 ones at this particular bit position, and since 2 is occurring once, so it is only contributing 1 0 to this position. Similarly, for this next bit position as well, 3 zeros are being contributed, whereas only 1 1 is being contributed. And here 3 zeros are being contributed from the 3 4s, and 1 0 is being contributed from the number 2. So you will see at every bit position, we will have either 3x plus 1 zeros, right? Or we will have 3x plus 1 ones, depending on the bit values of the number x, right? So these 3x, right? Since every number is appearing in a multiple of 3, so this x could be any common number, right? Basically will be depending on the numbers which are occurring thrice, and this will be the factor multiplied because each number is occurring thrice, right? So we will have this factor 3x factor because every number is occurring thrice for the bit positions, and this one factor will come because of a number which is uniquely occurring in the array, right? So using this observation, we will solve our question, right? So let's take this example only and continue forward, right? The elements are 4, 4 and 2, right? So when I write these again, right, what I can just simply do is I can take the sum of the bit values at every position, right? I can just take the sum of the bit values at every position. When I do this here, I get 3 as my sum, right? I get 3 as my sum, and when I take its mod by 3 only, I will reduce, or I will say get away from all the elements which are occurring thrice, right? I will get away from all these bits values. So when I take the mod with 3 of 3, I get a 0 here, right? Similarly, the process is followed here. When I take the sum, I get 1. I take a mod with 3, I get 1. So this bit, right, this bit which is here is presenting the bit which is actually left out, right? Because when I take the mod with 3, all the bits which are occurring thrice in a multiples of 3 are being cancelled out, and the only left bit here is 1, right? And here also, when I take the sum, I get 0, and when I take the mod with 3, I get 0 again, right? And when you get, and whatever sum or whatever, let's say the number you get in the end is actually the number which is occurring once, right? Here I get, when I take the sum of all the bit positions and then take a mod by 3, and in the end, which is the number which is being formed is here 2, and I can simply say that this is the number which is occurring once. Now, what will be the time complexity? You will see here that since we are, let's say we are taking n bit numbers, right? We are taking n bit numbers and we are going over each bit and calculating its sum. So the time complexity here is going to be order of n, right? And what about the space complexity? You will see here that let's say we are taking the only numbers or numbers up to 32 bits. So I can basically take an array. I can basically take an array of size 32 and store the bits or the sum of the bits after taking the mod at every ith index only. And since I am taking constant space of size 32, I can say that my space complexity is order of 32, which is equivalent to order of 1 only. So I am taking a constant space here to solve this question and a time complexity of order of n. I hope this question is clear to you. Thank you.
Hi guys, let's talk about the problem trailing zeros in factorial of n. As per the problem description, we are given an integer n and we have to return the number of trailing zeros in factorial of n. So please note that your solution should be in logarithmic time complexity. As per the problem constraints, n lies between 1 to int max, and in the example input we are given n as 5. The example output is 1 because the factorial of 5 is 120. Here there is only one trailing zero. So therefore we will simply return 1. Now what is a trailing zero? So if you look at here and if you say there are 3 trailing zeros, then you are wrong. Why? Because a trailing zero is the one which is at the rightmost end and that has no non-zero number to the right of it. So here there are only 2 trailing zeros. This will not be counted as a trailing zero. Let's see how can we approach this problem. So the brute force solution to this approach is that first we can calculate the factorial of n and then count trailing zeros in the result. So we can find the trailing zeros by repeatedly dividing the factorial by 10 till the remainder is 0. So what do we mean by that? So let's say the factorial, the n is equal to 10, and we'll do 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9 and into 10. This will give us the number as 3628800. Now to find the trailing zeros, we will simply mod it with 10 to get the last digit. So we will get 0. Now since this is 0, we will simply increment our count. Next, we will divide the number by 10 to check the next number, the next digit, that means this number. So after dividing it, we will get nothing but 362880. So that means this digit has been removed, the last digit. Now we have got this. Now in the next iteration, we will simply do the mod of it to get the last digit. We got it as 0. So again, we will increment the count. Next, we will divide it by 10. Right, so here we have divided it by 10. Again find the mod of it and we get a non-zero number. That means here we have to stop because we have found out all the trailing zeros. And since we have got a non-zero numbers, that means we do not care what is there at the left of it, right? So we will simply stop and return the count. And this is what written in this snippet, that we have got the factorial as 120 of 5 when n is 5. So we will run our loop till this factorial is greater than 0. So if f mod 10 is equal to 0, we will simply count it up and we will divide f by 10. And else if it's not 0, then we will simply break because we do not care what is there on the left, and we will simply return the count. But the problem with this approach is that the above method can cause overflow for even slightly bigger numbers, as the factorial of a number is a big number. So even if the number is as small as, let's say, 22, then it's going to cause overflow because the factorial of even a small number is so big that it is certain to cause overflow, right? Therefore, this method is not the appropriate one. So what should we do now? Let's see what is a better approach. So how can we find a trailing zero in any number? So when a number is multiplied by 10, we get a trailing zero, right? So let's see 24. If it's multiplied by 10, we get 240. So here we have got a trailing zero just because we have multiplied it by 10. Then we have, let's say, 240, and if we multiply it by 10, we get 2400. We have got another zero which is contributed by this 10. Right, so in 2400, if we do into 10, we will get 24,000. So another zero which is contributed by 10. So here there is an observation to make that a number, if multiplied by 10, it will give us a trailing zero. So for example, if n is equal to 10, then we'll get this as this is the factorial of 10. So 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9 into 10. The factorial is this, and we can see that there are two zeros, the two trailing zeros. That means there must be two tens, right? There must be number of tens is equal to 2 that are contributing to two zeros. So how are we getting that? So 1 10 is here and 1 10 is formed by the combination of 2 and 5. So if we multiply 2 and 5, we'll get 110, right? So this is 110 and we will get 110 from here. So that accounts to two zeros. So this tells us that if in a number we look at the number of pairs of 2 into 5, then we'll be able to count the number of trailing zeros. So if in a number we look at that how many number of 2's are there and how many number of 5's are there, then we take the smaller number, we take the smaller power of a number. Let's say 2 is x and 5 is y. So let's say y is smaller than x, then we will take this, the number of 5's, and that is going to be the answer. Why? Because let's see with the help of this example. So in this case, the power of 2 is 3. That means there are number of 2's as 3. So this is 1 and 2 into 2 gives us 4. So 1, 2, 3. So there are 2 3's and 5 is just 1, right? So 5 will pair up with a single 2 to form a 10. Therefore, we will look at a lesser power from between 2 and 5, right? Now, do we really need to find the power of 2? Do we really need to find a power of 2? Well, here the observation is to be made that if we carefully look, then every second number is a multiple of 2. and every fifth number is a multiple of 5. So if we are just able to find the power of 5, then they can pair up with that many number of 2's to produce a trailing 0. So let's look above with the help of example. So in this case, every alternative number, so this is a multiple of 2, then this is a multiple of 2, 6 is a multiple of 2, 8 is a multiple of 2, then 10 is a multiple of 2. So at every second number, we are able to find the multiple of 2, which will give us the number of 2's, right? That will give us the number of 2's. And every fifth number is going to be the multiple of 5 that will contribute to a power of 5, right? That will contribute to the power of 5. So as we can see that the number of multiples of 2 are greater than number of multiples of 5, that means we are going to get more number of 2's as compared to 5. So the number of 2's are going to be greater as compared to the number of 5. So we need not calculate the power of 2. Instead, we can simply calculate the number of 5's or the power of 5. So the problem has now reduced to finding the power of 5. So this is a generalized equation, like if we want to find a power of any number, then we can apply this formula. Here our x is equal to 5. So here we are actually trying to find the power of 5, and let this be any number, the remaining number which when multiplied with the power of 5 gives us factorial n. So how can we find the power of 5, or how can we calculate the number of 5? So for that purpose, we can simply take the floor of n by 5. For example, let's say n is equal to 11. Now n by 5 gives us 2.2. The floor of 2.2 is nothing but 2. That means the factorial of n is going to have 2 zeros. If we see here, then the factorial of 11 is nothing but 3991680. So there are 2 zeros, the 2 trailing zeros. Because in 11, how many multiples of 5 are there? It's 5 and 10. So this has contributed to 1 5 and this has contributed to 1 5. Therefore, the total number of 5's are 2, and therefore the trailing zeros are 2. But we are not through yet. Why? Because what about if n is equal to 28? What will happen in that case? So if n is equal to 28, so in 28 factorial, what are the multiples of 5? So the multiples of 5 are 5 itself, then 10, 15, 20 and 25. 5 will contribute to 1 5, then 10 will contribute to another 5, 15 another 5, 20 will also contribute to 1 5, but here 25 is going to contribute to 2 5's. So by taking floor of n by 5 with the formula n by 5 and taking floor of it, we'll get 1 5, right? So if we do n by 5, that means 28 by 5, this is going to give us 5 only, right? So that means here we are going to get just 5 zeros. But here we can see that there are 6 zeros in total. So for getting the left out 5, that means the 5 which is still to be counted, we'll have to divide it by next power of 5, which is 25. So now we actually have to calculate the power of 25. But now what about 128? So in that case, we'll get 125 as well in the multiples of 128 factorial, the multiples of 5 in 128 factorial. So it's going to be 5, 10, 15, then 20, 25, 30 and so on. Then 125 as well, right? So 125 has 3 number of 5's. So after dividing by 5 and then by 25, we'll still be left with one more 5. So for that, we'll have to divide it with the next power of 5, which is 125 to actually get the third 5. Now the formula has become, so the count of number of 5's in prime factors of n factorial, it's equal to floor of n by 5 plus floor of n by 25 plus the floor of n by 125 and so on till the number is greater than n by power of 5. So the time complexity of this approach is going to be order of log base 5n. What was the question? That we have to find a logarithmic time complexity, and we have actually achieved that. So why? Because we are incrementally dividing n by powers of 5. So first we are dividing n by 5, then n by 25, then n by 125, so on till n by 5 to the power k, which reduces to 1, and n by 5 to the power k is equal to 1. So n is equal to 5 to the power k. After taking log both sides, we will get k as log base 5n. That means log base 5n number of steps we have to take to get the solution, and therefore the time complexity is going to be order of log base 5n. So this was it. Let's talk about the problem anagrams. So given an array of strings, you have to return all groups of strings that are anagrams. Represent a group by a list of integers representing the index in the original list. Let's look at this sample case for clarification. So an anagram is a word, a phrase or name formed by rearranging the letters of another. For example, spar and rasp both are anagrams because they have same set of characters, the frequency of characters are same, but only the order is different, right? Also note that all input characters, all inputs will be in the lower case. So for example, the input is cat, dog, god and TCA. So you have to return 1, 4 and 2, 3. So basically we have cat over here, then dog, then god and TCA. So this is 1, 2, 3, 4. Right. So cat and TCA, they are anagrams because they have same set of characters. Even the frequency is same, but the order is different. Right. So we have taken them together. That means 1 and 4 are together. Likewise, dog and god, they both are anagrams because again the characters are same, the frequency is same, but the order is different. So 2 and 3 are anagrams. So we have to basically return the answer like this. Now here in the explanation it's written that cat and TC are anagrams which correspond to index 1 and 4. Dog and god are another set of anagrams which correspond to index 2 and 3. So the indices are 1 based. The first element has index 1 instead of 0. So let's see how can we approach this problem. So the solution approach is that we can sort the given strings. Now how does this intuition came? So basically from the question itself, it said that anagrams are the words that have different order of the same set of characters. So if we sort both the strings, then if those strings become equal, that means they are anagrams. Right, because the order was different only, but they have same characters. So if we sort them, then the strings which are anagrams will become equal. And after that, we can simply group them together. Right. So here we have got the input as act, DGO, DGO and act. So we have actually got them by sorting the individual strings given in the input. So ACT represents cat, DGO represents dog and DGO again represents god and ACT represents TCA. Right, so we have basically sorted them. Now we know that a group of anagrams can be represented by a key, which is nothing but the string we get after sorting characters present in those strings. Right, so here both cat and TCA are anagrams and they can be represented by a string which is ACT. So this we have got after sorting the characters present in them. So now to group the strings basically we can perform hashing. So how can we do that? So a key can be the string, right? This unique string. Here the group of anagram is cat and TCA, right? So we can have a unique string for them which is ACT. Likewise for dog and god we can have a unique string as DGO. So we can have a string and then we can have value as vector of int because we have to basically keep track of the indices of the anagrams, right? So now we will simply iterate over this array, the sorted array. So first we are at act, then act is not present in our map. So let's put the string, and the index present is 1. So let's put it in the vector. Right, now we are at DGO. Right, so DGO is also not present in the map. So let's put it in the map, and the frequency and the index present is 2. So let's put it in the vector. Now let's move ahead. So DGO is already present in the map. Now let's include the index. Right, so we have included 3. Now we are at the 4th position and act is already present in the map. So let's simply include the index. So here we have the set of anagrams represented by their indices. Now the only task is which is left, that is to iterate over them and store it in the vector. Right, so here we have vector 1 and 4, and we have a vector 2 and 3. So we will push them into a vector and we will simply return this in our answer. Right, also we will only put the vector in this resultant vector which have a size of greater than 1. Right, if a string has size of just, so if the vector has size of just 1, then that means there is no anagram present for that particular string. So we can simply ignore that. Right, so now for the time complexity, let's look at how we are going to sort the strings. So for sorting the string, basically we can perform counting sort. We are able to perform counting sort because here the range of characters is fixed, right, which is 26. So we have 26 characters, and therefore the complexity is going to be order of n into k, where n is the number of strings and k represents the length of the longest string. So the time complexity turns out to be order of n into k. Now, if we don't want to sort the strings up, then we have another approach as well. So we can actually maintain a frequency array. Right, now what is a frequency array? So let's suppose we have this as a string. To form a frequency array of this, we will have a character set. We will have an array of 26 characters which have a range from 0 to 225. So why 26? Because we are in the input we are given that only lowercase alphabets will be there. Right, so we maintain a frequency array of size 26. Now basically we will be mapping a small a to index 0, then small b to index 1, and so on, and we will be representing small z by index 25. So basically here we will be storing the frequency of all the characters. So frequency of 0 denotes that it is the frequency of character a, and so on. Here the frequency of a is nothing but 1. So we will put 1 over here. Then frequency, so basically we will be iterating over the string. So let's do that. So here b is there and frequency of b is nothing but 1. So at index 1 we will put 1. Now b is nothing but only 1. So let's put 1 at index 3. Right, then a is there, so let's put 1 at index 0. Then c is there, so let's put 1 at index 2, and e is there, so let's put 1 at index 4. Initially all will be initialized to 0. So here's how we have built this frequency array, and likewise we can do for this string as well. And if the frequency array of both these strings come out to be equal, that means they are anagrams of each other. And likewise we can check this for all the strings given in the array. So for this purpose we can basically have a map where the key can be, instead of string, it can be the vector of it. So here it represents the frequency array. The strings having the same frequency array will be pushed to the corresponding vector. So let's see how we will maintain this. So here we have cat, right? Frequency array for cat will look something like this. So here in this will be the key, right? Since this was not present, so first we will be pushing it, right? And then we will be placing this 1 over here. Then we will be moving on to dog, and frequency array of this will look something like this. And we will simply put 2 over here, right? Then we will move on to God, right? The frequency array of God will look something like this. So we will put 3 over here. And for TCA, the frequency array will look something like this. So we will put 4 over here. So that's how we can do it. And then the last thing left will be to simply iterate this. like we did previously and return the answer. The time complexity for this approach is going to be, so for creating frequency array for a string, it's going to be order of k, where k is the length of the string, and the total time complexity will be order of n into k, where n is the number of the strings, so it's going to be order of n into k. So this was it. Thank you so much.